So let's look at an example of using the rational root theorem to actually totally solve a polynomial equation. We're going to do everything we can with the rational root theorem. So I have this function up on the screen, 3x cubed minus 6x squared minus 90x plus 75. And we're going to do three things. We're going to first use the rational root theorem to find all of the possible rational roots. We're going to use those in synthetic division in part 2 to fully factor this polynomial, and then we're going to solve it. So the first thing I'm going to do is, hopefully my pencil won't die, right, we want to find our p's and our q's, right? So to do the rational root theorem, you want to take the constant term, which in this case is going to be 75. So we'll do part 1. Right, we're finding our possible rational roots. Okay, right, so our constant term is 75 here. And so there's a decent number of factors of 75, right? So 75 is 1 in 75. The next number that goes into it is 3 times 25. And then I can also do, I'm going to have to spread these out a little bit more, is 15 and 5. And then we're all done there. And then for our q, right, q is your leading coefficient. So q is 3, and the only terms here are 1 and 3. So for my possible rational roots, I like to do all of my p's over each q, so I like to do them one at a time. So I know for, there are 2 q values, so I'm just going to set these up. So I know in the denominators of all of my fractions are either going to be a 1 or a 3. I'm going to cheat and copy and paste. Okay, so my first p value is 1, so I can do 1 over 1 and 1 over 3. And then I'm all done with that one. And then I could do 3 over 1 and 3 over 3. So then my 3 is done. So then I'm moving on to 5. So I can do 5 over 1 and 5 over 3. Right, and then we just keep going, dividing each possible p value by both of the q values in this case. So 15 over 1 and 15 over 3. Oops. That's not what I wanted to do. Right, now I'm down to 25 over 1 and 25 over 3, and then finishing up with the 75. So then before I write my final list, we just want to simplify and take out duplicates. So for the first one, I have 1 over 1 is 1, so I have plus and minus 1 as an answer. 1 over 3 doesn't simplify, so plus and minus 1/3. Okay, 3 over 1 is 3, so that's a new one. And then 3 over 3 is, oh my god, 3 over 3 is 1, right? So that's a duplicate. Okay, and then I get 5 over 1 is 5, so plus and minus 5 is an option. 5/3 is a new one, so I can write that on my list. 15 over 1 is a new option. But then 15 over 3, right, that's 5, and I've already written that down, so that's done. 25 over 1 is a new answer, and so is 25/3. And then we also have 75 is a new one. I'm just going to resize this list so I can fit everything into one line. Right, and then 75 is also a new option. And then 75 over 3 is 25. So that one's no longer an option. So we're done part 1. We've listed all of the possible rational roots. So these are all the possible whole number and fraction x-intercepts for this function. So then for part 2, we're just going to start testing them with synthetic division to see which one works. So one thing I'm going to do beforehand, since I'm fully factoring anyway, I'm just going to rewrite the problem. And I'm I'm going to take my list of PRRs, right, because those are my possibilities that I'm going to be testing. So I'm just going to move them down so I can see them down here too. So one thing I noticed right off the bat is that this function has a GCF of 3. So I'm going to go ahead and factor the 3 out front because I want to fully factor anyway, so I'm going to have to do it eventually. So I'm going to pull out the 3. So then I'm going to just set up my synthetic division chart. So then I'm going to use the numbers that are inside my parentheses now. So I have 1, -2, -30, and 25. Okay. So I always start with 1 first because it's such an easy number to test. So, right, you drop the 1 down for the synthetic division. 1 times 1 is 1. Add to get -1. It's going to give me -1, -31, -31. Okay, that's not going to equal 0, so +1 is not an option. Okay, let's test -1 then. Okay, so if I multiply, I get -1. It's going to add to give me -3, 3, -27, 27. Okay, so -1 doesn't work. So the 1s are out. So I'm just doing this. I don't know what the answer is. I wrote the problem, but I don't, remember what it is, because I wrote it a couple days ago. So I always test my whole numbers first because I think the math is easier. So I'm going to test the 3 next. So drop the 1, multiply by 3. It's going to give me 1 times 3. Okay, that's definitely not going to give me +25, so +3 is out. Okay, let's test -3 then. Okay, so that's going to add to give me -5. Okay, that's going to give me +15. It's going to give me -15. Well, that would give me +45. Okay, so that's not going to give an answer. Okay, so 1's out, 3's are out. Okay, let's test the 5's then. Okay, so 5. 5 times 1 is 5. Adding gives me 3. It's going to give me 15. It's going to give me -15. It's going to give me -75. Okay, that's not going to work. +5 is out. Okay, let's test -5 then. So we got -5. It's -7. Okay, that's +35. Oh, I think this is going to work. It's going to add to give me +5 back, and 5 times -5 is -25. Woohoo! We found one that works. Okay, so if x equals -5 is the root, the x-intercept, that tells me that x plus 5 is the factor. So right now, for my function, for my factoring, we have h of x equals the GCF of 3 times the factor we just found, x plus 5, and then because I'm a big color coder, I'm just going to change that color to purple. Right, then we have our leftover equation. If we put the x's back in, that would have been x squared minus 7x plus 5. So then my goal right now is just to factor. So I want to see if x squared minus 7x plus 5 is factorable. Right, so I want to multiply to 5 and add to -7. Well, the only factors of 5 are 1 and 5, and I can't make a -7 out of those. So this is prime, it's not factorable, which means that this is my final answer, right? This is my fully factored answer. So then we're going to take that fully factored answer and use that to solve h of x equals 0. Right, so I'm just going to set my factored answer equal to 0, and then once I want to solve it in factored form, all I'm going to do is set each part equal to 0, right? So 3 equals 0, well, 3 never equals 0, so there's no solution there. Then I'm going to set x plus 5 equal to 0, and we already know what the answer is there because we found it in the synthetic division table of -5, so there's one answer. And then we're going to set our quadratic factor equal to 0. So since I know it's not factorable, it's a prime quadratic, I have to use the quadratic formula to solve it. So write, just as a little refresher, write x equals negative of b plus or minus the square root of b squared, did not get myself enough room, minus 4 times a times c, all over 2 times a. So I'm going to find the discriminant first, the stuff under the square root. So my discriminant is going to be negative 7 squared minus 4 times my a value is 1 and c is 5. So negative 7 squared is negative 7 times negative 7. Well, that's positive 49. And I wrote c instead of 5. Oops. Okay, so 4 times 1 is 4, and 4 times 5 is 20. So this is 49 minus 20. So that gives me a discriminant of 29. So then when I go to solve this, I'm going to use my quadratic formula. So x equals the opposite of b. So opposite of negative 7 plus or minus the square root of my discriminant all over 2 times my a value of 1. So x is going to equal negative of negative 7 is positive 7 plus or minus the square root of 29. And then 2 times 1 is 2. And 29 is prime, so I can't break down the square root of it at all. So that's actually going to be my other two answers.